for giving me this opportunity to speak. And today, as Dr. Paul mentioned, I'll be talking about dark energy and specifically using 21 centimeter intensity mapping, and also talk about a project that we're leading at UKZN, but with many international and national partners to pursue this avenue. And the project is called HIRAX. So before I start, I just wanted to say a belated happy 60th birthday to Sunil. And yeah, so here's a paper that we kind of put out that was a consequence of my master's work. So I was a master's student with Sunil as my co-supervisor, and I realized this is my first and only paper, so maybe we need to write another paper, Sunil. And Sunil is as many of you may know, if you know Sunil well, he's more than just an academic colleague and collaborator. There are many kind of fun times that we've shared together. He's inspired many lively dinners and parties, and as you can see from this wedding picture, is more than just an academic colleague and mentor. And I was thinking, Sunil, I think I know you now for about 30 years. So even as youthful as I am, it's already been 30 years that we know each other. So yeah, it's been great, and many more happy years. And I guess we're all sorry that it is belated, but such are the times that we live in. So yeah, enjoy the rest of the conference, Sunil. So yeah, so I'll move on to my outline. I'm gonna this talk, and I should apologize for those who've heard some version of it recently. I've been giving this talk at a few conferences. Yeah, it's mostly focused on observational cosmology. So in the spirit of what Roy did this morning with the SK Observatory, I'm going to look at dark energy and talk specifically about baryon acoustic oscillations as a probe of dark energy. And then beyond measuring these BAOs using galaxy surveys, we can use intensity mapping using the 21 centimeter line in the radio to actually map out these BAOs. I'll talk about the HIRAX instrument as a realization of this kind of program. And then I'll talk about the forecasts with HIRAX. So yes, so we've had many talks during this conference about dark energy, what it could be, more on the theoretical side. And so this talk is kind of complementary to that, in that we're focusing on how we can actually try to constrain the properties of dark energy, and thereby, maybe rule out or confirm some of these dark energy models. Related to HIRAX, I should also mention, I mean, these have been given already, but Amanda spoke about FRBs with, HIRAX, and Warren Naidu also gave a talk on HIRAX cross correlations with the CMB. So yes, so moving on to my first part of my talk, dark energy and baryon acoustic oscillations. So yeah, so this is familiar, to most of you. You would have heard a lot about the cosmic history of the universe with different talks focusing on different epochs. The main one that I should mention, and well, I guess here, looking back to the last scattering surface, we see fluctuations in the cosmic microwave background. Those fluctuations that are also present in the matter grow, so structure forms as these irregularities grow. And then structure formation is halted at late times because dark energy comes to dominate and accelerates the expansion of the universe. So that's a kind of single slide summary of the cosmic history. Underlying it, there's a lot of kind of puzzles, as speakers have alluded to in this conference. We can use the cosmic microwave background as it's a very powerful probe of cosmology. And so here's a kind of map shown by Planck. So these CMB anisotropies tell us that in the early universe, there were fluctuations. And it's these fluctuations that grow into the large-scale structure that we see, the fluctuations in corresponding fluctuations in the matter. We can use these observations to measure the power spectrum, the angular power spectrum, with very high precision. And I'm also involved in a project, the Atacama Cosmology Telescope, that maps these fluctuations out to much larger multipoles. We've seen the power spectrum and multipoles in previous talks. And the physics is actually quite simple. It's linear, so it's easy to describe. The CMB spectrum has lots of features in it, which allows us to constrain many different parameters. And the underlying model is nothing more than a harmonic oscillator and acoustic oscillations from that damped driven harmonic oscillator. So the reason I mentioned this is because the baryon acoustic oscillations that I'll talk about later basically arise from the same physics. And here we're seeing these oscillations in the radiation, but we also have observed them in the matter distribution because baryons are coupled to the cosmic microwave background radiation. There's an imprint that's left in the baryon distribution. So these observations have led us to kind of cosmic concordance, even though there's some, as people have mentioned, some inconsistencies, which as the data gets more and more refined, may lead to interesting new physics. And so what we find is a universe which largely is dominated by dark energy, making up about 70% of the universe. So we can ask the question, what is this dark energy? We've first observed it through its effect on the accelerated expansion of the universe, but there are other ways to observe it that I'll talk about in a short while. But from a theoretical point of view, we heard talks earlier this week by Claudia de Ram about the large kind of zoo of models that kind of explain dark energy, and it may not even be a new field, but it could also be our theory of gravity, which is breaking down on large scales. So people have spoken about modified gravity, and there's this is probably one of the most perplexing problems in cosmology today, if not all of physics, and it's really something that is exciting but also quite challenging. And so one way so we know very little about dark energy apart from the energy density today and equation of state, but we'd like to know more properties of the dark energy in order to constrain these theoretical models that try to explain it. And so we can approach this. So the approach we're taking in this talk is how can we measure the properties of dark energy? What are the key observational probes? And I mentioned so the supernova, they were first used to detect the cosmic acceleration. So here with the supernova, we measure the luminosity distance. Cosmic lensing, so Nick Kaiser spoke about lensing, and you can use this probe as to measure the shear over large scales in the universe, and that constrains the growth factor because it's related to this amount of structure, and because you're measuring distortions of the propagation of photons, you also get information on the angular diameter distance. You can also use galaxy clusters, so you can develop or build up large surveys of galaxy clusters. Again, these are rely on structure formation, so you measure the growth factor, and then you counting them, so you're measuring basically the co-moving volume. And so those are three techniques, all of which are being pursued through large cosmological surveys. And the one I'm going to focus on today is baryon acoustic oscillations. Here, basically, in the angular direction, you measure the angular diameter distance, and then from the radial measurements of the BAO, you get the Hubble parameter. And so this image just shows the different probes being very complementary to each other. So this motivates us adopting these various approaches from an observational point of view. So baryon acoustic oscillations, let me just start this video. Right, so if we have an initial overdensity in the very early universe in which matter and radiation were coupled, in particular baryons and the cosmic background photons, this overdensity propagates out at the sound speed, and then at the decoupling era, so roughly a few 100,000 years after the beginning, photons separate from the baryons, and this outgoing wave basically dumps all the baryons at a specific physical scale, about 150 megaparsecs. And so we can actually go and look for the scale in the distribution of matter today. So on the scale, you'll get a slight excess in the density of galaxies. So just moving on. Sorry about that. Yeah. So galaxies trace the matter distribution. So we can go out and count galaxies and map them out in 3 dimensions. And what we find is that we see the slight overdensity in the that comes from these baryon acoustic oscillations on the 150 megaparsec scale. And this is shown here, the Sloan 3 data. So what's shown here on the bottom right is the baryon acoustic oscillations, both in physical coordinates. So this shows the peak in the galaxy distribution or the correlation function, basically at 100 H inverse megaparsecs. This is shown for 3 different redshift bins. So there's a convincing detection of this feature. And then if you Fourier transform this and measure this in the power spectrum space, you will see these series of oscillations. So these are the so-called baryon acoustic oscillations. This is obtained by measuring the 3-dimensional galaxy positions. Yeah, we basically have a unique length scale, this 150 megaparsecs, which we can use as a kind of standard ruler to map out cosmology. So we can, yeah, measure the distance. So we can use the BAOs to give us a distance ladder. So here's recent results from the Ebos experiment. And basically, well, firstly, I should mention that these are coming from different galaxies, different types of galaxies that are mapped out more efficiently at different redshifts. So at the high end, using the Lyman alpha forest and quasars, and at the low end, using luminous red galaxies. So this sample is quite heterogeneous, but Sloan, with these measurements, we are approaching distance scale measurements at the few percent level. So this is basically DV, which is a combination of the angular diameter distance and the Hubble parameter. So we have a few percent level measurements of the distance ladder or distance scale from these BAOs, and we can then turn that into cosmological constraints. The results I spoke about, I've mentioned here, are from actually conducting galaxy surveys, different types of galaxies. But we can approach this problem in a different way. Galaxy surveys are quite expensive. You need to obtain spectra for each of these galaxies, and that's a very expensive exercise because you need to bring your shot noise down. You need to actually measure lots and lots of galaxies. So intensity mapping is a kind of cheaper kind of approach to this, where you actually don't resolve. You're not interested in resolving these galaxies. And let me explain this now. So firstly, these galaxies are not just traced by the visible light, traced out by the visible light, but also by the hydrogen. So hydrogen is a fuel, that gives rise to stars, and we can actually use neutral hydrogen and emission from this neutral hydrogen to map out the galaxies, and the galaxies in turn, trace in a biased way the matter distribution. So this is just a simulation showing that the neutral hydrogen traces the gas, which in turn traces the dark matter. And Roy mentioned this earlier today, talking about the spin flip transition. So when the electron changes its spin from pedal to anti-pedal, it emits a 21 centimeter photon. And so we can use this emission. It's very weak, but by building telescopes with large collecting areas, we can actually detect these photons. And there's a large amount of hydrogen in the universe that we can measure the signal from. And the advantage of this, even though the signal is weak, is that we get a precise redshift. So the redshift almost comes for free because this is a line intensity mapping survey. we don't have to follow up and observe again to get the redshift of the hydrogen gas. We get that for free. So that's what makes this technique quite competitive. And so this is just explaining why we can kind of throw away actually resolving galaxies, and that's where the saving comes from. So the main point here is that I mentioned the 150 megaparsec scale. This is about a degree on the sky. So that's quite a large scale. If you look at the galaxy distribution, it's basically the scale corresponding to this yellow circle. And what you'll realize is that if we want to measure this scale, we don't need very high resolution or spatial resolution or angular resolution. We need a resolution which is maybe a bit smaller than the scale, but not as high as a resolution as good as 1 megaparsec or less, which is the typical scale of galaxies. So we don't need such high resolution. So what we can do is we can basically average all the galaxies in this region, and that's shown here. So if we can map out the hydrogen with very low resolution, this allows us to actually now trade off and measure very large volumes very efficiently. So without caring about the individual galaxies. And there's a trade-off, as Roy kept referring to, and I'll talk about that now. With not being able to resolve these galaxies. So we use this intensity mapping technique, and as you can see, the scale is very large. So we need large volumes to beat down the cosmic variance. So this scale is about 150 megaparsecs. So the intensity mapping surveys that we're proposing are, correspond to volumes which are of the order of 50 to 100 gigaparsec cubed. So that's the trade-off, and we can manage this trade-off by not resolving galaxies. Right. So we need to go out to high redshift or a large redshift range and cover large areas on the sky to build up this volume. But if we do so, then we can use the peak, the BAO acoustic oscillations as a standard ruler for charting the expansion history. And that's where our constraints on dark energy will come from. So this signal has been detected. It's been detected in cross correlation, though, not in auto correlation. So the kind of race is on to try to measure this. But in getting to that kind of milestone, there's a significant challenge that we need to overcome, which is removing galactic foregrounds that are very bright in the radio. And here, that challenge is overcome because those foregrounds don't correlate with the galaxy density, so they actually drop out. And that's why in cross correlation, the measurement is significantly easier. So yeah, what are the challenges for this 21 centimeter intensity detection? The signal is weak, so you need lots of collecting area and you need very sensitive receivers. So this is at the level of a millikelvin. Just to give you a sense, and maybe skipping ahead to my last bullet point there, the foregrounds are galactic and extragalactic are extremely bright. They're significantly larger than the 21 centimeter signal, so they're at the level of tens of Kelvin. So you're talking about 4 orders of magnitude to actually do that, to remove the foregrounds. You need large volumes, as I mentioned, to reduce the cosmic variance. So that means large sky areas and a large redshift range. And you need a very stable instrument to calibrate the observations. So if your calibration is not precise, then you run the risk of leaking foregrounds, or foregrounds contaminating your signal. And to actually remove these foregrounds, in addition to a stable instrument, you also need a very well characterized instrument. So you need to actually, build a telescope that's characterized with high precision. So things like the telescope beams, the response, the frequency response, all of those things need to be very well characterized. Otherwise, you run the risk of leaking, having foregrounds contaminate the 21 centimeter signal. I'll talk a bit more about this shortly. So how do we go about designing such a telescope? So we want to maximize sensitivity on scales of interest. So the scales are large scales, a degree or more. So we need a compact array geometry. So with an interferometer, and I'll talk about this on the next slide, the further apart you pull your dishes, the higher resolution you obtain. But as I mentioned, we're not interested in resolution. We're more interested in surface brightness sensitivity. We need a large redshift range. So something, as I'll talk about HIRAX next, HIRAX will observe from redshift 0.8 to 2.5. And that is basically capturing the dark, the era of dark energy coming to dominate the cosmic expansion. And so this is a frequency range corresponding to 400 to 800 megahertz. We need to actually resolve the 150 megaparsec BAO scale in the angular direction. So that corresponds to resolutions of 1.3 to 3 degrees over this frequency range. And that gives us baseline lengths of about 15 to 60 meters. So that's consistent with having a very compact array. And the BAO scale along the line of sight, so you need to resolve that in the radial direction. And that corresponds to something like 12 to 20 megahertz at these frequencies. So that requires a very good frequency resolution. So you need lots of channels, measuring the signal over lots of channels, unlike, for example, CMB experiments, where they have, broad bandwidth and, just a single channel across that band. Here we need, at least 100 channels, more like 1,000 channels, to measure the higher order BAO peaks and detect foregrounds. And then finally, the BAO signal is quite small. It's about 0.1 of a millikelvin. So you need a low system temperature. Very, as low noise as possible detectors, and you need large collecting area. And just to contrast this approach, just to contrast this approach with traditional radio interferometers, where the goal is basically, to get good resolution, you need long baselines. And shown here is Meerkat and the baseline coverage for Meerkat. And the layout is actually optimized for better imaging. So you sample the so-called UV plane, very densely, and you then Meerkat, for example, can trace structure on small to intermediate scales. So shown here is an image of the bullet cluster with Meerkat, and you can see both small scale features and intermediate scale features. For example, this diffuse emission in the galaxy cluster. So this intensity mapping is quite different from traditional radio interferometers, or at least how they are designed. So moving on to describe the HIRAX instrument. So this is I've basically sketched out the parameters. So the goal is to build 1,000 6-meter dishes. It's a scalable array, so we've basically funded for at least 128 elements and possibly 256. And then we'd like to secure more funding to build out to 1,000 elements. Of course, there are many challenges that are we have to overcome along the way, which other intensity mapping experiments are also facing, and that's why the scaled approach is can be quite powerful in overcoming these challenges before we move on to the next stage. The dishes are stationary, so that keeps them cheap. They're not mechanized, but they can tilt for more sky area, and we're basically working with companies in South Africa to fabricate them here. And the back end, there's a strong overlap with Chime. So Chime has developed a lot of the technology in terms of ice boards and doing the channelization and digitization, and then the cross correlation with GPUs. But we've improved that technology subsequently. So the collaboration and funding shown here are all the partner institutes, and I won't go into too much detail here, but basically we funded through UKZN and NRF contributions, and also Swiss and Canadian contributions to the back end. So we've got enough budget to build at least the first and second stages of the array. Where is it located? In the Kuru Desert, so very close to Meerkat. So shown here is this image here on the top right is the SK radio telescope. So that's where Meerkat is, and we are basically on the road to Meerkat. The good thing about it is that being there gives us infrastructure. So along this road, there's a very an excellent there's a power and data line that runs to SK or Meerkat. And so we tap into that. There's roads, special road that's being built. And so we in a very remote area, but we have access to the infrastructure. And shown here, and this is kind of, I think Amanda showed this previously, but shown here is our band, and the RFI contamination is, almost negligible. So we're hoping, to get excellent data in this band. And the other advantage being in the south is that we have access to southern skies, and people have spoken, I think Roy previously and Warren before that, about cross correlations, and we can, cross correlate HIRAX data with ACT or the Simons Observatory, and also with LSST, and then the spectroscopic surveys, the satellites that the southern regions of their southern regions that they're mapping out. So the design plan, we're going to have these close pack 6-meter dishes. We've manufactured fiberglass and metal prototypes. I'll show you some pictures of that. We've got a dual polarized cloverleaf feed, and we're carrying the signal over optical fiber to the back end. And these FPGA ice boards that are made at McGill, basically digitize and channelize the signal, and then working with our Swiss partners and Canadian Toronto partners, we've built the GPU X engine. So that'll do the cross correlation, the interferometric cross correlation. So we've already set up a prototype array, which we've been using for the last few years, basically to kind of debug our systems. These were 8 off-the-shelf, dishes which didn't have the right focal ratio. We've subsequently built, and shown here is a picture of the fiberglass dish that we built with a local South African company. And we've now in the stage of basically putting out on tender, or putting out bids, or call for bids for 256 of these dishes. And I should mention, in addition to Hartrow, there's complementary efforts going on in Canada and in the US, and even in Switzerland now. So we do, we've observed with the prototype array, we can see fringes, we can fit basic beam and gain models. The RFI environment at Hartbeespoort, which is just outside Johannesburg, so the site here is very poor. There's a lot of RFI from the city itself. So we're planning to move to the Crew, a qualification array site, to test out, the new dishes. And we're still developing and testing our electronic, the RF system at Hartrow. So now I'll talk about dark energy with HIRAX. What constraints do we expect? And then, of course, what is a foreground challenge? So shown here, and so this is a nice picture that's taken from Phil Bull's paper. Shown here are the, and this relates to the question Warren asked earlier about interferometers and single dishes. So these are the scales that interferometers can access compared to single dish. So, and just looking at the numbers here, the angular coverage is basically limited by the primary beam, which is set by the size of the dish. And the smaller scale you can resolve is set by the maximum baseline. Because this is a compact array, our largest scale is 6 meters, and the beam, the dish size is 6 meters. So our largest scale is a few hundred meters. So it doesn't give us very high resolution, as I mentioned before. And then in the so this is in the K perpendicular direction, which corresponds, for a given redshift, you can translate that into an angular scale. And then in the parallel direction, so looking along the line of sight, if you decompose the parallel direction into line of sight modes, these are so-called K parallel modes. And there we're limited by foregrounds, because foregrounds remove the, removing foregrounds will take out the lowest K parallel modes. I'll speak a bit more about that now. And on the large, so they at high K, we're limited by non-linearities. So that tells us, which scales we can probe. I should also mention we're planning to map out a survey area of about 15,000 square degrees and a redshift from 0.8 to 2.5. So we can now measure or talk about measuring how well we can measure the angular power spectrum, and I'm showing it in this K parallel, K perpendicular space. So these are kind of forecasts that Warren has done. So splitting up the redshift range of HIRAX into 4 bins, you can see that we can get very high precision measurements. So each of these pixels corresponds to a signal to noise of about between 20 and 50. And so, the detection of the BAOs will be, many thousands of in signal to noise. And so we can turn those measurements into very precise constraints on the baryon acoustic oscillations. So shown here is the baryon acoustic oscillation feature with the smooth, so the power spectrum divided with the smooth power spectrum scaled out. And what you can see is that with Hyrax 128, we get pretty competitive constraints, and with 1024, the constraints are really excellent. So we'll measure the matter power spectrum in the BAO regime, right? And I indicated the scales that we're limited to here, right here. So we can't go to very large scales, as Roy pointed out, and we can't go to very small scales. So we kind of optimized to pick up just the BAO scale. So we can then turn those into distance scale forecasts, and I think Amanda showed this plot previously. So with the Hyrax 1024, we're getting a few percent constraints, and going out from redshift 0.8 to 2.5. I showed you the Ebos results, and the nice thing about the 21 centimeter intensity mapping is that we're using it's a kind of homogeneous survey. We're using the same types, galaxies or same objects to trace out the distance scale, whereas here you're using many different types of galaxies which would have different systematics. And then Roy has mentioned DESI and Euclid, and these surveys will of course be carried out by those experiments. So the take home here is that we can measure the distance scale at the percent level out to quite high redshifts. You can turn that into parameter forecasts, cosmological parameter forecasts, and here Devin Crichton postdoc has made these plots. So we'll constrain cosmological parameters quite significantly. So this is with a Planck prior, and then importantly, thinking about dark energy, our figure of merit, which is basically the inverse area, traced out in this contour plot of the dark energy W naught equation of state parameter, so the constant bit W naught, and then the redshift bit. So this is in this kind of Linde parameterization. So this measures the change of the equation of state with redshift. We basically get a figure of merit of about 300, and these are this is approaching the stage 4 galaxy surveys that we mentioned, DESI and Euclid. And so shown here is the latest kind of state-of-the-art constraints on W naught and WA. And I think the figure of merit here is on the order of about, I think it's 50 or 60, if I'm not mistaken. It depends. I think without Planck priors, it's about 30, and with Planck priors, it's about 90. So yeah, so that's what Hyrax will do in terms of dark energy constraints. I just wanted to check, Bikash, how many minutes do I have left?
5 minutes more.
Okay, all right. So I'll just quickly talk about foregrounds, and then I'll stop and take some questions. So yeah, so the way we actually get rid of foregrounds, which are, as I mentioned, 4 orders of magnitude higher than the signal, is if you look here as a function of frequency, you can see that the foreground structure is quite smooth, whereas the 21 centimeter structure is quite noisy. And that's basically, if you look in a given direction in the sky, you see the 21, these clouds of hydrogen emitting the signal at kind of almost in a random kind of way. You map or in a very noisy way. So there's no coherence in the frequency direction, whereas the foregrounds are quite coherent. So we use this coherence to actually filter out. So you can basically do a high pass filter and taking advantage of the spectral smoothness of this foreground intensity spectrum. And when you do that, and this is of course in the ideal case, you can see that you can actually remove a lot of the signal. So the signal drops from many tens or 100 of Kelvin to something like on the order of tens of microkelvin, and that is below the 21 centimeter signal. And in this filtering process, because this is a small scale structure, you don't actually take away too much of it. So you can get significantly high signal to noise. So so that's how we would remove the foregrounds. Of course, there's a price you pay, and that's basically you lose your large-scale radial modes. So these modes which are smooth across the whole frequency band, and that's shown here in the vanishing of these the signal to noise at these low K parallel modes, so 0.01 inverse megaparsecs and below. So the foreground challenge, and I'll just briefly go through this, but basically we've the visibility of which is the quantity we measure, is basically just looking at the non-perturbative terms, is the instrument times the sky modes. These are the ALNs of the sky, and your instrument converts it into a visibility, by summing over L, etc. If we perturb the instrument, and this is where the challenge comes in, and if we perturb the foreground, so we assume that we don't know the foregrounds perfectly, and we don't know our instrument perfectly, then what you find is that you get this main component here, which you can filter out because you know that well, but then you get leakage terms which come from not knowing your foregrounds well enough and not knowing your instrument well enough. And these leakage terms can be quite significant compared to the signal that you're trying to trace out. So what this is saying is that you really need very precise modeling of the foregrounds and a very precise characterization of the instrument. So we need to characterize our beams, our pointing, the delay, between the different interferometer signals coming in, our gain, bandpass, and cross polarization. So this really represents a significant challenge. And shown here is a plot where if you make an error of 1% in your beam, the foreground wedge, really starts to build up, and you basically lose all your sensitivity to the BAOs. So I think a lot of work we've been doing in the collaboration has been focused on this. How do we build an instrument that's really well characterized so that can remove these foregrounds? And so we've been involved with beam calibration using holography and using drones. We've been developing techniques for doing the quasi-redundant calibration of telescopes, and we've been performing simulations to set tolerances on our telescope parameters so that we can limit the instrumental leakage. So this is just a cartoon of these simulations that we've been busy with, and Devin Crichton has been kind of spearheading this along with Warren and others. So we've got this kind of end-to-end pipeline where we can basically model the instrument and then look at non-idealities in the instrument and how they basically leak foregrounds. And shown here, for example, is a constraint that we derive on the placement of the focus, so how well the feeds are actually placed. And you see if they're at the centimeter level, then already we start picking up systematic errors that are larger than our statistical errors. So we actually need to build a really precise instrument. And so I think I'll stop there.